Mechanical testing in oil and gas for inspectors and weld engineers, ensuring safety through precise industrial material evaluation. Mechanical testing in oil and gas. Introduction: Why mechanical testing matters, mechanical testing versus service failure, code standards landscape, tensile testing overview, tensile properties, stress, strain curve, impact testing, Charpy, ductile versus brittle fracture, hardness testing overview, Brunel, Rockwell, Vickers hardness methods, bend testing, compression testing, fatigue testing, creep testing, stress rupture testing, torsion testing, proof load testing, microstructure examination. Macro etch testing, weld versus base metal testing, common mechanical failures, test selection guide, inspector's role, key takeaways. Mechanical testing plays a foundational role in ensuring the structural integrity, safety, and long-term performance of materials and welded components used throughout the oil and gas industry. Inspectors and weld engineers routinely rely on mechanical testing evidence to validate compliance with governing codes, project specifications, and regulatory requirements. In environments characterized by high pressure, elevated temperatures, corrosive media, and cyclic operational loads, understanding the mechanical behavior of materials becomes essential to preventing catastrophic failures. This introduction reinforces why mechanical testing exists as a critical risk mitigation pillar. It enables engineers to confirm that a material's mechanical properties, such as strength, ductility, and toughness, are adequate for service conditions. Beyond raw data, mechanical testing also provides insights into manufacturing quality, weld soundness, the effectiveness of heat treatments, and the stability of microstructures. In oil and gas applications, components often face demanding combinations of load, environment, and temperature. Therefore, testing helps ensure that both base metals and welds exhibit resilience and predictable behavior under stress. Additionally, inspectors use mechanical testing to detect deviations early, reducing the likelihood of in-service anomalies like brittle fracture, fatigue cracking, or time-dependent deformation. This presentation establishes a comprehensive foundation for mechanical testing by outlining common test types, how these tests relate to field performance, and what inspectors should look for in lab reports. It emphasizes the necessity of understanding material response to ensure safe operation of pipelines, pressure vessels, offshore structures, rotating equipment, and safety-critical assemblies. Through systematic review, this session equips inspectors and weld engineers with the knowledge to interpret test results confidently and correlate them with compliance criteria and real-world mechanical demands. Mechanical testing is essential in the oil and gas sector because it directly supports asset integrity, personnel safety, and regulatory compliance. Inspectors and weld engineers must understand that visual inspection alone cannot reveal how a material will behave under pressure, temperature variations, or prolonged cyclic loading. Mechanical tests quantify the inherent properties of metals, providing measurable indices such as tensile strength, yield strength, ductility, hardness, and toughness, each vital for determining whether a component can withstand the harsh operational conditions typical of upstream, midstream, and downstream installations. In many historical incidents, pipeline ruptures, vessel failures, and offshore structural collapses have been traced to inadequate mechanical properties, improper welding practices, or substandard fabrication processes. Mechanical testing also matters because it supports validation of manufacturing processes such as heat treatment, welding procedure qualification, and alloy verification. Toughness testing, for instance, protects assets from brittle fracture at low temperatures. Hardness testing helps prevent hydrogen-assisted cracking in weldments. Tensile tests ensure that strength levels meet ASME design expectations. Without these checks, even minor deviations in metallurgy or improper heat input could create latent defects that only appear once equipment enters service. In short, mechanical testing is the last line of defense before commissioning assets that operate in safety-critical conditions. Service failures in oil and gas environments can arise from multiple factors including high internal pressure, extreme temperature fluctuations, corrosive exposure, hydrogen charging, and cyclic loads that induce fatigue. Mechanical testing provides the data needed to predict how materials will respond to these conditions. Inspectors must recognize the correlation between laboratory-generated material properties and how components behave in the field. For instance, insufficient yield strength can lead to plastic deformation of pipelines under pressure surges, low impact toughness can result in brittle fracture during cold starts, and inadequate fatigue strength may lead to crack initiation in rotating or pressure cycling equipment. Mechanical tests also help engineers model the probability of failure using real mechanical data rather than assumptions. In environments containing hydrogen or sour service media, materials must be carefully evaluated to ensure they do not embrittle or crack prematurely. By comparing test outcomes against code-mandated minimums, inspectors can ensure that equipment possesses the necessary resilience to operate safely. Mechanical testing thus transforms unknown performance risks into measurable parameters that allow for informed engineering judgment. In oil and gas projects, understanding the hierarchy and applicability of standards is crucial for inspectors and weld engineers. ASTM standards primarily define how tests must be conducted, ensuring consistency, accuracy, and repeatability across laboratories. ASME codes, including Section 2, Section 8, and B31.3, provide the acceptance criteria and govern which mechanical properties must be satisfied for pressure-retaining equipment and piping systems. ISO standards, widely accepted for international projects, often harmonize with ASTM but may differ in specimen dimensions or methodology. Inspectors must be able to differentiate between these documents to verify that testing procedures align with specification requirements. For example, a tensile test might be performed using ASTM E8, while the acceptance criteria for minimum ultimate tensile strength, UTS, or elongation may come from ASME Section 2 Part D. Similarly, Charpy impact testing may follow ASTM E23, yet acceptance decisions rely on project specifications or ISO 15614 for weld procedures. This interplay between testing standards and acceptance codes is fundamental for compliance, and inspectors must verify both alignment and correct interpretation. Tensile testing is one of the most widely used mechanical tests for evaluating the strength and ductility of base metals and welded materials. For oil and gas applications, it is particularly important because pressure-containing components must withstand high stresses without permanent deformation or fracture. Tensile testing involves applying a uniaxial load to a standardized specimen until failure, generating key data such as yield strength, ultimate tensile strength, and elongation. These parameters allow inspectors and weld engineers to verify that materials meet the minimum design values outlined in ASME and project specifications. Tensile testing is essential during procedure qualification records, PQRS, where it confirms that welding procedures produce weld metal and heat-affected zones with acceptable properties. The process also ensures that base metals delivered to site comply with mill certificates and fabrication requirements. For critical components such as pipeline steel, offshore structure members, and pressure vessel plates, tensile tests serve as a primary acceptance gate. Inspectors should be able to interpret tensile reports, check compliance with specified testing standards, and confirm that specimen orientation, gauge length, and testing rates conform to ASTM E8 or equivalent methods. Tensile properties describe the strength and deformation behavior of metals under load, and they form a core part of acceptance criteria in oil and gas applications. Yield strength, YS, defines the stress level at which a material begins to plastically deform, an important consideration for pressure-retaining components that must remain within elastic limits under normal operation. Ultimate tensile strength, UTS, indicates the maximum stress a material can withstand before necking begins, and is often used to classify material grades. Elongation, expressed as a percentage, measures ductility and shows the material's ability to stretch before fracture, reflecting toughness and resistance to sudden failure. Reduction of area, RA, is another indicator of ductility, revealing how much the cross-section shrinks at the fracture point. Inspectors must correlate these properties with design expectations. High YS prevents excessive deformation, adequate UTS maintains structural capacity, and good elongation ensures resilience against brittle behavior. By reviewing tensile results, weld engineers confirm that welding procedures produce acceptable mechanical properties across the weld metal and heat-affected zones. These properties together help determine whether a material can safely endure service loads. The stress-strain curve provides a graphical summary of a material's response to tensile loading and is a critical interpretation tool for inspectors and weld engineers. In the elastic region, the material deforms proportionally to the applied load and will return to its original shape upon unloading. Once the yield point is reached, plastic deformation begins, indicating permanent changes in shape. Understanding the transition between elastic and plastic behavior is important when evaluating pressure-containing equipment because exceeding yield limits in service can lead to unacceptable deformation or progressive damage. Beyond the yield point, the curve rises to the ultimate tensile strength, after which necking begins and deformation localizes until fracture occurs. Inspectors must be familiar with curve interpretation to verify whether unusual shapes, such as discontinuous yielding or serrated flow, signal metallurgical anomalies, improper heat treatment, or material defects. The curve is also essential when reviewing laboratory reports or comparing results during weld procedure qualification. A clear understanding of the stress-strain relationship enables inspectors to identify deviations early and correlate them with operational risks. Charpy impact testing measures a material's ability to absorb energy during fracture and is essential for preventing brittle failures in oil and gas environments, especially under low temperature or dynamic loading conditions. Materials with insufficient toughness may fracture suddenly without visible deformation, posing catastrophic risks for pipelines, offshore structures, cryogenic systems, and pressure vessels that experience low ambient temperatures. The Charpy test evaluates the energy absorbed by a notched specimen when struck by a swinging pendulum. The resulting impact energy reflects the material's ductility and crack arrest capability. Inspectors should understand how test temperature affects results, as many materials exhibit reduced toughness at lower temperatures. Project specifications often mandate minimum impact values at designated test temperatures such as -20 degrees Celsius, -29 degrees Celsius, or -46 degrees Celsius, depending on service conditions. During weld qualification, impact tests are performed on both weld metal and heat-affected zones, ensuring that welding does not reduce toughness below acceptable limits. Inspectors must verify compliance with ASTM E23, check fracture appearance percentages, and confirm that specimens are oriented correctly relative to the rolling direction. Understanding the distinction between ductile and brittle fracture is essential when assessing material suitability for oil and gas applications. Ductile fracture is characterized by significant plastic deformation prior to failure, typically providing visible warning signs such as necking or bulging. Brittle fracture, in contrast, occurs suddenly with little or no prior deformation, often propagating rapidly and catastrophically. This type of failure is particularly dangerous in low-temperature environments or when materials possess defects, improper microstructures, or inadequate toughness. Inspectors must be able to identify fracture appearance in failed components during investigations. Ductile fractures show fibrous, dimpled surfaces, whereas brittle fractures display cleavage planes with shiny, granular textures. Mechanical testing, especially impact testing, helps quantify susceptibility to brittle failure. Low impact energy or high hardness indicates increased brittleness. In welded components, improper heat input or rapid cooling can increase the risk of brittle fracture by forming hard or unstable microstructures. By understanding fracture modes, inspectors can assess mechanical test results more accurately and ensure compliance with project requirements for ductility and toughness. Hardness testing provides an indirect yet valuable measurement of material strength and is frequently used in oil-gas inspection because of its speed and versatility. Hardness correlates with yield strength, tensile strength, and resistance to wear or indentation. In welded components, hardness values are particularly important because excessively high hardness in the weld or heat-affected zone can lead to hydrogen-induced cracking, a common failure mechanism in sour service and high-strength steels. Inspectors often utilize hardness testing during welding procedure qualification, post-weld heat treatment verification, and in-service inspections. Hardness readings help evaluate whether heat treatment achieved the desired metallurgical transformation and whether welds meet hardness limits specified in NACE. ASME, or project specifications. Portable hardness testers allow field measurements on components such as pipelines, pressure vessels, valves, and structural supports, providing rapid assessment without removing material. Understanding hardness testing is crucial for ensuring that metallurgical conditions remain stable and safe throughout equipment life. Hardness testing methods vary in load application, indenter type, and suitable material ranges. Brinell hardness testing uses a hardened steel or carbide ball indenter and applies heavy loads, making it ideal for coarse-grained or softer metals such as pipeline steels and structural components. Rockwell hardness testing offers quick results using different scales, such as B and C scale, making it widely used for general engineering applications and quality control checks. Vickers hardness testing, with its diamond pyramidal indenter, is versatile and suitable for welded materials because it allows precise measurement of narrow heat-affected zones. Inspectors must choose the appropriate hardness method based on test objectives, material type, and required resolution. For weld inspection, Vickers is often preferred to map hardness gradients and confirm compliance with limits for sour service or high-strength steel applications. Hardness results also help detect fabrication issues such as improper heat treatment, excessive work hardening, or undesirable microstructures. Understanding the strengths of each method enables inspectors to interpret results accurately and ensure that components meet required mechanical property thresholds. Bend testing evaluates the ductility and soundness of welded joints by subjecting specimens to bending stresses until failure or a specific deformation limit is reached. This test is particularly important during welding procedure qualification, where it confirms that weld metal and heat-affected zones can deform without cracking. Guided bend tests are commonly used, applying force to bend the specimen around a mandrel. Inspectors evaluate the tension surface for cracks, lack of fusion, inclusions, or other discontinuities that compromise weld integrity. Bend tests help ensure that welds possess adequate ductility and do not contain flaws that could propagate under load. One of the advantages of bend testing is that it examines the entire weld cross-section, offering a holistic view of weld quality. Inspectors must review bend test results for both face and root bends, confirming compliance with acceptance criteria defined by ASME, AWS, or project specifications. By understanding bend test outcomes, inspectors can determine whether welding procedures produce sound, ductile joints suitable for service. Compression testing evaluates material behavior under compressive loads and is typically used for brittle or non-ductile materials where tensile testing may not be appropriate. In oil and gas settings, compression testing applies to materials such as refractories, certain cast irons, or cementitious components in well integrity applications. The test helps determine compressive strength, modulus of elasticity, and failure modes under applied loads. While not commonly required for standard metallic pipeline or pressure vessel steels, compression testing is relevant when evaluating specialty components subject to crushing or compressive bearing loads. Inspectors may encounter compression testing during evaluation of structural supports, non-metallic components, or specialized equipment. Understanding the principles of compression behavior helps inspectors interpret results when working with materials outside typical ductile steel categories. Fatigue testing assesses a material's resistance to failure under repeated cyclic loading, a critical consideration for applications involving pressure fluctuations, vibration, or rotating machinery. In the oil and gas industry, fatigue failures can occur in offshore structures, compressor systems, pumps, and pipelines subjected to pressure cycling. Fatigue tests generate S/N curves, stress versus number of cycles, that characterize material endurance limits. Inspectors must understand that fatigue failure often occurs below the yield strength, meaning that materials can fail even when stresses remain within elastic limits. Fatigue behavior is highly sensitive to surface condition. Weld quality, residual stresses, and stress concentrators such as notches or geometric discontinuities. Welded joints are particularly vulnerable due to inherent weld toe stress concentrations. Inspectors should correlate fatigue test data with weld quality, ensuring proper profile, smooth transitions, and absence of defects. Understanding fatigue testing enables inspectors to anticipate potential risks and enforce requirements that reduce the likelihood of cyclic-induced failures. Creep testing examines the deformation of materials subjected to constant load at elevated temperatures over long durations. This behavior is particularly relevant in refinery heaters, reformer tubes, power generation components, and any equipment operating in the creep range of materials. Creep is a time-dependent phenomenon and can lead to gradual deformation, loss of dimensional stability, and eventual rupture. Inspectors must understand creep test results when evaluating components exposed to sustained high temperatures, ensuring that materials possess the necessary creep strength to maintain integrity throughout the equipment's service life. Creep curves illustrate three stages: primary, decelerating; secondary, steady state; and tertiary, accelerating, leading to failure. During procedure qualification or material selection, creep testing ensures that alloy compositions and heat treatments are suitable for long-term high-temperature exposure. This helps prevent failures such as bulging, tube thinning, or catastrophic rupture in high-temperature service. Stress rupture testing evaluates a material's time to failure under constant stress and temperature conditions, providing insight into long-term durability in high-temperature applications. Unlike creep tests that emphasize deformation rate, stress rupture testing focuses on the point at which material failure occurs. In oil-gas facilities, components such as furnace tubes, reactors, and steam-exposed assemblies rely heavily on stress rupture performance to ensure longevity. Stress rupture results help determine whether materials possess adequate metallurgical stability, grain structure, and alloying elements to withstand prolonged exposure to elevated temperatures. Inspectors may encounter stress rupture data when reviewing material certifications for high-temperature service equipment. Understanding the correlation between stress, temperature, and rupture time allows inspectors to verify that selected materials will not fail prematurely under expected operating conditions. This ensures reliability, reduces downtime risks, and enhances safety in thermally demanding environments. Torsion testing measures material behavior under rotational shear loads and is commonly applied to components such as shafts, fasteners, couplings, and torsional drive elements found in oil and gas machinery. This test helps determine shear strength, ductility, modulus of rigidity, and failure characteristics under twisting forces. Inspectors and weld engineers must recognize that torsional loading can differ significantly from axial tension or compression, leading to unique failure modes such as shear cracking or torsional buckling. Torsion tests assist in evaluating whether materials or welded joints can withstand twisting motions encountered in rotating equipment such as pumps, compressors, drilling tools, and mechanical drive trains. Understanding torsion behavior enables inspectors to assess suitability of materials in service conditions involving misalignment, vibration, or torque spikes, thereby ensuring reliability and operational safety. Proof load testing verifies that components, particularly fasteners, can withstand a specified load without experiencing permanent deformation. In oil and gas applications, this is crucial for bolted flange joints, structural connections, and critical equipment assemblies. Proof testing ensures that bolts, studs, and other fasteners possess adequate strength and ductility to maintain joint integrity under pressure and thermal cycling. Unlike destructive testing, proof load testing applies stress below the material's yield point, confirming elastic performance while preserving the component. Inspectors must verify that procedures follow applicable standards and that results demonstrate compliance with project specifications. Properly conducted proof load tests help prevent bolt relaxation, leakage, or catastrophic joint failures in pressure-containing systems. Microstructure examination provides detailed insight into a material's internal structure, enabling inspectors and weld engineers to understand how grain size, phase distribution, and metallurgical transformations influence mechanical properties. Using optical or electron microscopy, examiners can detect undesirable microstructures such as excessive carbide precipitation, grain boundary sensitization, martensite formation, or improper phase balance. In the oil and gas industry, microstructure evaluation is crucial for validating heat treatments, ensuring weld quality, and confirming alloy integrity. For instance, fine equiaxed grains generally indicate good toughness, while coarse grains may lead to brittle behavior. Inspectors should be familiar with microstructural indicators that correlate with mechanical test results, ensuring that laboratory findings align with expected material behavior. By understanding microstructural characteristics, inspectors can diagnose root causes of mechanical failures and verify that materials meet required metallurgical conditions before service. Macro-etch testing provides a low-magnification view of weld profiles, fusion characteristics, and internal structures by chemically etching polished samples. This method reveals welding anomalies such as lack of fusion, incomplete penetration, porosity distributions, grain flow, and weld bead geometry. Macro-etching is widely used in welding procedure qualification to ensure that welding processes produce acceptable penetration and fusion across the joint. Inspectors evaluate etched samples for alignment of weld passes, uniformity, and evidence of structural soundness. This method is particularly beneficial for identifying defects not visible on the surface or those that may not appear on radiographic or ultrasonic examinations. Understanding macro-etch results helps inspectors verify that welding procedures produce consistent and reliable welds suitable for service in demanding oil and gas environments. Welds and base metals exhibit different mechanical behaviors due to differences in microstructure, heat input, and metallurgical transformations. As such, they require distinct acceptance criteria during mechanical testing. Base metals are typically more homogeneous, while welds include weld metal, heat-affected zones, and varying thermal histories. Inspectors and weld engineers must recognize that toughness, hardness, and ductility can vary significantly across these regions. During procedure qualification records, PQRS, mechanical tests such as tensile, impact, and bend tests must confirm that welded joints meet project-specified minimums. Weld testing often includes additional requirements, such as hardness mapping, to ensure weld stability and resistance to cracking. By understanding the mechanical differences between weld and base metal, inspectors can evaluate test results more effectively and confirm that welding procedures produce joints that are safe for service. Mechanical failures in oil and gas equipment often originate from insufficient toughness, excessive hardness, inadequate ductility, or improper heat treatment. Examples include brittle fracture due to low impact energy, hydrogen-induced cracking in welds, fatigue failure caused by cyclic loading, and creep rupture at high temperatures. Inspectors must recognize how mechanical test results correlate with failure mechanisms. High hardness values may indicate susceptibility to cracking, while low elongation or poor reduction of area suggests brittleness or inadequate ductility. Understanding failure modes allows inspectors to identify deviations early, preventing serious operational incidents. Reviewing mechanical test documentation helps ensure that materials and welds possess the required properties to withstand service conditions, thereby enhancing reliability and reducing downtime. Selecting the correct mechanical test is essential for ensuring that materials and welds meet the demands of their intended service conditions. Tensile tests verify strength for pressure-containing components, impact tests assess toughness for low-temperature applications, fatigue tests evaluate suitability under cyclic loading, and creep tests confirm performance at high temperatures. Hardness testing provides quick verification of heat treatment and weld quality. Inspectors must understand how each test correlates with potential failure mechanisms and service conditions. For example, pipelines operating at low temperatures require impact testing, while rotating machinery exposed to vibration demands consideration of fatigue strength. By selecting the appropriate test based on service factors, inspectors can ensure materials meet required performance levels and mitigate operational risks. Inspectors play a critical role in verifying that mechanical testing procedures, results, and documentation comply with applicable standards and project requirements. This includes reviewing laboratory test reports, validating specimen identification and orientation, confirming adherence to ASTM or ISO test methods, and ensuring that acceptance criteria are evaluated according to ASME or project specifications. Inspectors must also verify that laboratories are accredited, equipment is calibrated, and results are consistent with expected material behavior. Understanding mechanical properties enables inspectors to detect anomalies and raise technical queries when results appear inconsistent or outside normal ranges. Through rigorous review, inspectors help prevent failures and ensure that only compliant materials and welds enter service. Mechanical testing is a vital element of engineering assurance within the oil and gas sector, providing measurable indicators of material strength, ductility, toughness, and long-term performance. Inspectors and weld engineers must understand how these properties correlate with in-service behavior to prevent failures such as brittle fracture, fatigue cracking, and creep deformation. By mastering mechanical test methods, interpreting results accurately, and applying acceptance criteria correctly, inspectors ensure the safe operation of pressure equipment, pipelines, offshore structures, and welded assemblies. This presentation emphasized the importance of tensile, impact, hardness, bend, fatigue, creep, torsion, and microstructural examinations, highlighting their relevance to real-world service conditions. Ultimately, mechanical testing empowers engineers to make informed decisions that protect assets, personnel, and the environment.